And in fact, in the general knowledge, you can talk about like that. In different reference frame A and B, reference frame means like we will say relative to what? Relative to frame A or frame B. In this case, one of the frame is water. So relative frame A, water, or another frame is ground, relative to the ground. Okay. So that's a reference frame. When we're talking about the motion, we have to specify the reference frame. Or more, okay, you can think about that's the Cartesian coordinates we use to do the calculation. So, but the Cartesian coordinates can be Cartesian coordinates stay there, the ground. It can also be a Cartesian coordinates moving with something, like moving with water or moving with a tree. Okay, so, but in any case, if you have the two frame A and B, you can talk about the velocity for a particular point, like P. Okay, so VPA is point P, the boat, the velocity of the boat relative to A, for example, the ground, and VPB is the velocity of the object, the boat, relative to another frame, water, like that. Okay. So there is a straightforward relationship. The velocity of the boat relative to the water equals to the velocity of the boat relative to the ground equals to the velocity of the boat relative to the water plus the velocity of the water relative to the ground. So you can see the relationship here. VPA equals to VPB plus VBA. Okay? But this shows that sometimes you may need to do the vector addition if they are not along the same direction, like this case. Okay. And this is actually called the Galileo addition of the velocity. That's a rule to combine velocity from different reference frame. Okay, it's named after Galileo because he's the first one to say this is a general rule. And if we want to consider the acceleration, the relationship is that acceleration will be the same for different frame. Okay, either we are talking about the motion relative to the water or the motion relative to the ground, acceleration will be the same. Okay, this is called the Galilean principle of relativity. Laws of mechanics in all inertial reference frame will be the same, right? Perfect. Okay. It has to be the sentence and finish. Okay. This relativity, Galilean principle of relativity says that laws of the mechanics in all initial reference frame will be the same. Okay. In fact, what do we mean by the laws of mechanics in here? The most important thing is F equals to ma. And it will take the same form because you can see it depends on the acceleration. Acceleration will be the same in different frame, so this equation is the same in different frame. If it depends on the velocity, it wouldn't be the same and different reference frame. Okay. But please note that, precisely speaking, we are talking about inertial frame, not a non-inertial frame. Okay. Inertial frame, like this is frame moving with a constant velocity. If the frame is still in acceleration, then it's called a non-inertial frame. These things doesn't code for non-inertial frame. Okay. But of course, the point is that why should we choose non-inertial frame? In most cases, we don't want to choose non-inertial frame. Okay, we're just talking about the inertial frame. The reference frame moving with constant velocity. Okay, it can be a state frame like a ground. It can be a moving frame like the water. but it shouldn't be an accelerated motion. Okay. So let's just talking about the inertial free. And one thing I would like to comment is that these things are actually related to the basic structure of the time, of the space and time. Okay. The reason why we have Galilean addition of the velocity is that we live in a world of 3D space and 1D time. So here, the time, the one-dimensional time, is independent with three-dimensional space. Time is independent with the space. Because this, you can you can use the Galilean addition of the velocity. In fact, after you learn the calculus, you can try to think about this way. Velocity is simply dv dt. Okay, so that velocity is just with dx dt. So that equation, the velocity addition, Galilean velocity, is actually dxpa over dt equals to dx pb over dt plus dx ba over dt. Okay. So you can see that you measure the distance, the position at different frame, okay, and then you take the derivative with respect to the time, and you get this. And you can see you can do that. If you have xpab equal to xpb plus xba, and then you take the derivative with respect to t, you get this. And of course you can do that because t doesn't depend on the reference frame. You always have the same time, right? And different reference frames, so you can get this. So this means that the simple addition rule is actually a result of the independence between the space and time. Okay. Okay. So that's the basic structure of the space and time. And to complete the description of mechanics, we also need to have to identify the basic structure of the dynamics. We use the Newton's law of motion to describe the motion. Okay. And we know that Newton's law of motion satisfies the Galilean principle of relativity. It has the same form and different inertial reference frame. Okay. So you can see that the two rules named after Galilean actually characterize the basic structure of the mechanics. Galilean additional velocity characterizes the basic structure of space and time, and Galilean principle of relativity characterizes the basic structure of dynamics. So if we try to establish a new dynamics, new mechanics, then we have to examine how can we change the two things, the basic structure of the space of time or basic structure of the dynamics. Okay. So in fact, the new mechanics theory of relativity keeps the basic structure of the dynamics and change the basic structure of space and time. We can see how it comes. One of the important things in the history of the modern physics is to find out the speed of the light. Okay, there is an interesting phenomenon of the speed of light. It says that the speed of light in vacuum is the same in all inertial free. Okay, it's a constant. C equals to 3 times 10 to the power of 8 meter per second. It's very large speed. Actually, it's the largest maximum speed in our universe. Okay, this statement has been verified by the experiment, the famous Michelson-Malay experiment in 1881. It also can be calculated from Maxwell equation. That's theory, the fundamental equation to describe all the electricity and magnetism phenomena. Okay. So we believe this is true, but that's a disaster for the classical physics. Think about it. We say that at two different frames, the velocity should be different. VPA should be different with VPB because you have to add the velocity of the frame. The frame may not move, but the speed of light doesn't satisfy that. Okay? So if you send out a beam of light from the ground or send out a beam of light from a moving rocket, say, the result of the speed of light should still be the same. Okay? It seems that the moving rocket doesn't produce any effect to the speed of the light. So that's completely contradicts to the Galileo addition of the velocity.
Are there any theories as to why that is? Are there any theories as to why that actually is?
Yes. The theory is the theory of relativity, Einstein's spatial theory of relativity. So the whole theory is, in fact, you can see, trying to explain why. Okay, but this is a very long story. We cannot cover it here. But just that's the starting point of Einstein's spatial theory of relativity. How can you construct a theory to give you the same speed of light and all reference speed, all moving reference speed? But roughly speaking, we can compare it with the old theories like this. In the new theory, Einstein's spatial theory of relativity, it says that space and time are not independent. Okay, we live in a four-dimensional space-time. Okay, the time is actually interacting with the space. And now you can see that if the time is not independent, you wouldn't get the simple form. Okay, the velocity addition wouldn't be 1 plus 1 not give you enough. You will get a very complicated addition rule, characterized by relativity speed addition of velocity. Okay, it's very complicated. But this complicated calculation will give you the result for speed of the light. And any reference frame, it will give you the same velocity after some more complicated construction. So, and Einstein still keeps the basic structure of dynamics, the spatial relativity, which says that the law of the mechanics will still be the same in all the reference frame. Okay. And the new theory, Einstein's new theory produced a lot of new concepts for us, completely changed our common sense for the space, time, and matter and energy. Okay. So the new theory is very interesting. For example, we say that the length of any object is not, you don't have an absolute length for it. It actually depends on the motion or the reference frame. So if a ruler, like say, I have a 1 meter ruler, okay, but only if I measure it from a stationary reference frame. If in a moving reference frame, is the ruler actually moving, it will be less than 1 meter. It will change. Okay, the length will be contracted for motion. The faster the motion, the shorter the length. Also, no absolute time. Time is dilated for a motion object. Okay, so like 1 second, if in a stationary frame, you measure some time interval 1 second. But in a moving frame, maybe 2 seconds or 2 years. Okay, depends on the velocity. So that's a time dilation, okay? It's of course related to the time travel, if you can change the time by motion. And also no absolute simultaneity, okay? If two things happen at the same time in one reference frame, but they may not happen at the same time when looking at from another reference frame, okay? More important result for the spatial theory of relativity is the mass is actually equivalent with energy, given by the famous E equals to mc squared equation. Okay, any mass can be converted to the energy with this equation. Please note that C is a very large constant. It's the maximum speed of the universe. And C squared is a huge astronomical number. So any mass is related to the huge amount of energy. Okay. So it's kind of point out the probability for the some for atomic bomb. Okay, A bomb and H bomb. How can we get this kind of super bomb? Because we can try to for some nuclear reaction, we can try to change the mass, okay? And then the change, okay, when you get rid of the mass, you will release a huge amount of energy. So that's why we have this kind of super bomb. Okay. In fact, all energy comes from the mass change, even in the normal process. We just couldn't notice the small mass change. So we think that energy is independent with mass. In fact, it's not. Okay. So that's spatial relativity. Okay. Let's see. We probably have no time to go through the example here. And